Okay, so we have seen how to compute contour integrals. We have defined formally the idea of a contour integral for a function of a complex variable, and we saw some examples where, so in general, these contour integrals would depend on the path that is taken, right? So if you're looking at some integral f of z dz, and if you're going from a point A to B, the precise path that you take is going to have an effect on the value of such an integral. Now, in this lecture, we look at a few examples and see, is this a generic feature, or are there certain special circumstances in which it's only the starting point and the ending point that counts, and the details of the path are not so important. So let's look at a few examples in this lecture. Okay, so let's start with an example where we have the very simple integrand. It's just z. So if you take the integrand z, and I wish to do a contour integral of this function f of z is equal to z from a point z1 to z2. So I will fix z1 to be just the origin and z2 to be 1 plus I, and I will evaluate this contour integral considering a few different paths, and we will see whether the value is going to be different. Okay, first path that I wish to consider is represented here pictorially. So I need to go from the origin to the point B, which is 1, 1, right, in the xy plane. So I want to go from 0 to 1 plus I. So suppose I take the path along the x-axis, along the real axis, from 0 to 1, and then I turn in a direction perpendicular to the x-axis upwards, and then I go along this path A to B and cover a distance of 1 along this direction. So that's going to land me at the final destination, right? So if I break my contour into these two sort of piecewise nice paths and evaluate this integral along these two paths, then I have considering OA. So I see that y is a constant as far as this path O to A is concerned, and y is 0. So dy is equal to 0. If I write z as x plus iy, and y is equal to 0, so basically z is equal to x as far as the path 0 to A is concerned, which means I can replace z by x and I can replace dz by dx, and x of course goes from 0 to 1. So, but on the other hand, for the piece A to B, it is x that is a constant, and it's a constant held fixed at 1, x equal to 1, and so dx of course 0, and z in this case would be, in place of x plus iy, I can write it as 1 plus iy because x is equal to 1, and dz is just I dy, right? So I have to be careful about dz and d for different paths, and in this case there's an I times dy, right? So I have to carefully work this out, and therefore the contour integral can be thought of these two different regular integrals. So the first stretch is going to be just integral 0 to 1. In place of z I just put x, so in place of dz I just put dx, and for the second part y goes from 0 to 1, and in place of z I write down 1 plus iy, and in place of dz I write I dy. So I can go ahead and evaluate both these integrals. These definite integrals are straightforward to evaluate. So I get x squared by 2 from 0 to 1, which is just 1/2. Then plus I times, in place of I times 1, when I integrate it out, I get I times y. And then I squared becomes a minus y, so it's minus y squared by 2. And the limits are 0 to 1. So I get 1/2 from the first term, then plus I, and then a minus half. So if I add all of this carefully, it's just I. So this is the value of the contour integral if I take this path along 0 to A and then A to B. Now let's evaluate the same integral. So the integrand is the same, and the starting point and the ending point are the same, but I take a different path. Suppose I take this alternate path. which is first if I go along the y direction up to the point 0, 1, and then I take a right turn and go to point B in a direction parallel to the real axis. So if I were to take this path, then once again I can argue that as far as the path 0 to C is concerned, x is a constant here, and it is exactly 0 in fact. So therefore z is going to be just I times y, and dz is just I dy because dx is 0. And on the path C to B, it is y that is a constant and it's fixed at 1. So z is equal to 1 plus, so x plus I times y is x plus I in this case, and dz is nothing but dx, right? So this time the contour integral again is made up of two regular integrals which I have to sum, and here it's going to be 0 to 1 I times y, I times dy. So because I times y for this path is z, and I dy is dz, and the second integral is going to be 0 to 1 x plus I times dx. And if I go ahead and evaluate this, which is straightforward to do, I squared is minus 1, so I have a minus y squared over 2, 0 to 1, plus x squared by 2 plus I times x 0 to 1, which yields minus 1/2 plus 1/2 plus I, and I'm done. So once again I find that the answer is I. So the contributions from the different stretches are different, but they somehow add up to give me the same answer. So now we seem to be finding that this kind of a contour integral for this type of an integrand seems to not care about the path. At least we have verified that for these two paths that we looked at, the answer is the same. So let's look at one more path to see if this is indeed a generic feature. So suppose we were to take the path which is a straight line from 0 to B. If we were to directly go from 0 to B, right? This, as the crow flies, or the straight line path between 0 and B. If we took this path, then for this path x is equal to y. So z can be written as just x plus ix, and dz is in fact dx times 1 plus I. Therefore the contour integral is now given by integral z dz, but z is x times 1 plus I, and dx times 1 plus I is dz. So we just simply have this 1 plus I the whole squared, which I can pull out, it's just a constant, and 1 plus I the whole squared is 1 plus 2I plus I squared, and then the integral is simply just 0 to 1 x dx, which is straightforward to evaluate. But I notice that 1 plus I squared is 0, so it's just 2I times x squared by 2 evaluated from 0 to 1, which gives me just a half, and which cancels with the 2 outside, and so I'm left with I. So indeed for this path also I find that the contour integral gives me the same answer. So we observe that for these three different paths that we tested, the contour integral for this particular integrand is the same. It gives me I. So in fact it can be shown for this particular function it would be the same even for much more complicated paths. You can try it out, you can check this on your own, but there is a way to argue for this from a more sort of general perspective, right? So but we will go to that a little bit later. But let's try and carry out the same type of example but for a slightly different integrand. Suppose that's the content of example 2. Suppose instead of integrating z dz, suppose we were to do this integral of z star dz and go from z1 to z2 but along these three different paths. Now let's see what happens. So path 1 is when you go along the x-axis first, and then you take a perpendicular direction, you turn left and go up. So in this case we get integral 0 to 1 x dx plus integral 0 to 1 minus I bar. So I have to do z star, and then in place of dz of course I write I dy, just like what we did in the previous example. Now if I evaluate this, I get x squared by 2, so that gives me a half. Then I have iy plus y squared by 2 evaluated from 0 to 1, so I get a half plus I plus half, which is 1 plus I. But if I were to go along path 2, now I have in the direction from in the segment OC, I have z star is going to be minus iy, then I have dz is of course I dy, then in place of x plus I will have to write down x minus I, because I have to do z star, then I have a dx. So if I evaluate this carefully, so minus I squared will become 1, so I have a y squared by 2, and I have an x squared by 2 minus ix evaluated between 0 and 1. I get half plus half minus I, which is 1 minus I. So I immediately see that in fact the value I get for path 1 and path 2 are different. Path 1 gives me 1 plus I, path 2 gives me 1 minus I. So for completeness, let's also quickly evaluate z star dz along the third path, which is to take a straight line path. So now I have x times 1 minus I because it's z star, and then dx into 1 plus I remains as it is. So now it's 1 minus I into 1 plus I is 1 minus I squared. So that's going to be just 1 minus minus 1, which is 2. And integral 0 to 1 x dx just gives me x squared by 2 between 0 and 1, which is just 2 times 1 by 2, which is just 1. Right, so indeed, so it is it's indeed different from both of these well, all the three paths give you three different answers: 1 plus I, 1 minus I, and 1. Therefore, clearly the contour integral, as far as this integral is concerned, is heavily path dependent. So we see that, well, I mean, we have already seen examples where the path does count. So for sure, the path does count, as we might expect without doing any calculation. We might think that, contour integral, of course, is defined along a certain path, so we would expect that its value should depend on the path. But we have also seen examples where apparently it does not depend on the details of the path. So what are these special functions and these special paths where the path becomes irrelevant, right? So we will come to this, we will discuss this in some detail later on, but we want to look at one more example where in fact we will see that you can also deform these contours. It's not just about going from a certain point to another point. So let's look at what happens when you have a closed path and you deform this path, and give you an example where this deformation leaves the contour integral unchanged. So we have this example where we want to evaluate integral z to the n dz, and you take a closed contour which surrounds the origin, right? So where of course this n, it's important that n is a positive integer, right? So if you don't have a positive integer, then the answer can be different. So suppose you have a positive integer and we evaluate this contour integral, and let's say we consider a circular path of radius r centered around the origin. It's easy to consider a circular path. It's convenient to carry out this integral. That's why I'm looking at a circular path of radius r. So if I have a circular path of radius r, then I can write z as r times e to the I theta, and so immediately dz is just r times e to the I theta times I d theta. So the contour integral can be written as just a simple definite integral, where in place of z to the n dz, I write it as 0 to 2 pi, right? So the contour integral becomes just a definite integral in terms of theta. So now r times e to the I theta the whole power, and r is not changing, only theta is the only variable which changes. So I have r times e to the I theta the whole power n times r times e to the I theta times I d theta. So now integral 0 to 2 pi, so r to the n e to the I n theta r e to the I theta I d theta, and then I can pull out this r to the n plus 1 outside. I also comes out. Then it's just this integral 0 to 2 pi e to the I n plus 1 theta d theta, which I can integrate out and write down explicitly the answer, which is e to the I n plus 1 theta divided by I times n plus 1, going from 0 to 2 pi, which is immediately seen to be 0 because n is a positive integer. So n is a positive integer, and so this is going to give me the same, and theta at 0, theta at 2 pi, it's going to be the same, right? So these things don't even matter, right? So it's all about just this quantity and the fact that you're going from 0 to 2 pi. So indeed, this quantity is just zero. This contour integral, this closed contour integral is a zero if n is a positive integer, and it simply does not care about the radius r. So in fact, the result is much more general for this kind of a in integrand, a closed contour integral of this kind. Any closed path which surrounds the origin is going to be zero, which we can show, right? It does not matter, how complicated the path is, as long as it traverses around the origin, in some closed path, it's going to be zero, right? So there is a powerful theorem which all this discussion is leading up to, and in fact we are also going to exploit the Green's theorem, which we already discussed. We sort of took a detour into the Green's theorem, into a discussion of the Green's theorem, and now we are getting back to our study of contour integrals, but with the aid of these examples we are slowly building up towards an important powerful theorem which is called the Cauchy theorem, and the properties of analytic functions will again become crucial. So that's coming up later on, right? But as far as this lecture is concerned, it's just to show you that we can find examples where there is path independence as far as contour integrals are concerned, but generically speaking, contour integral by its very nature is a path dependent quantity. Okay, thank you.